Hi, this is Kaushal Patil. I'm a student of Masters in Computer Science program at University of Illinois Chicago, and I'm going to be showcasing my project 3 for course Distributed Objects for Cloud Computing. We start with the README, and this is the introduction. And I have described what the project basically does. We create a game, which is the Police Thief Catch Me game, and we create a client program for it. And we have also created an AWS Lambda that uses grpc's protobuf. The REST API is deployed on EC2, and it mentions that this is for the course project. Now, as far as the requirements fulfilled for Homework 3 are, we have created RESTful API. We have the AWS Lambda for the bonus grpc part. We have deployed the API on AWS EC2. We have created a client that uses multiple strategies. We have used regional and query graphs. We have used the confidence scores and valuable data in API and in client. I have provided the discussion for strategies towards the end. I have used Docker Compose for easy deployment. I have added unit tests, logging and config files, and I have used AWS S3 to retrieve graph files and store winner counts. These are the clone instructions for the project. Now let's talk about the workflow of this application. So it starts, we have already deployed the API on the EC2 server, so that server is running. And then we can start playing the game. So the client starts the simulation with adding the parameters and the graph files. So the simulation is run for X number of times for Y turns, and that is seen as the first step of this diagram. The second step is where the client program sends requests to the server and the server responds back, and this is the game loop. The client uses multiple strategies as defined by the user to run the game on the server, and basically we get the game runs and we have some output for the game result. So an agent can win. It can be like police, thief, or the game ends in a draw. Once the game ends, the winner information is sent to Lambda function over HTTP call, and the data in this call uses grpc's protobuf. The Lambda function then decodes the data in the HTTP call using the protobuf stub that it has, and the data after it's decoded is stored in a S3 file, which is the win counts JSON. Once the client program finishes execution, we can extract log files produced by the client program and go to the website deployed on Vercel to visualize this and the gameplay. So basically, whatever once in the gameplay that the client plays, we log what the game states were, and these game states are used to visualize what the police and thief agents did during this gameplay on the browser in our website. And this is the explanation of what I just said. So these are the components of the project. We have a repository which contains the REST API, which was created using Akka HTTP, and we have the following endpoints as you can see on your screen. The API also follows inspiration from the gym environments that are created for reinforcement learning games. Then we have a client that uses multiple strategies. The base strategies are random, chase enemy, chase valuable, and then we have added probability for exploration and using confidence in the strategies. Then we have the code for the Lambda function, which basically decodes and encodes the grpc request and response and interacts with the server. And then we have a thief police visualization file that basically can read the log files and visualize what happened during the gameplay. So I'll explain the REST API here. So we have the features for the REST API, that it is a graph-based game environment. We use both the query graph and the regional graph. It's a RESTful API. We can do asynchronous and concurrent processing because we have Akka actors, and I have created Docker and Docker Compose files for easy deployment. And these are the following routes. And you can also visit the Postman collection to view that in detail. And then this is how you can start the API on a server. We can either do SBT run, or we can also do run it using the Docker file. Then we come to the client. The client is a simple Scala program that we can provide arguments, program arguments to configure it. So basically, police strategy, thief strategy, turns for each player, simulation iterations, and then it can start the game simulation with the strategy as defined in the program argument. So these are the various strategies that we have. We have base strategies. Base strategy is like a random move. Chase enemy node is it chases the closest node to the enemy agent, moves to the closest node to the enemy agent. Chase valuable data, targets, it moves to the closest node with the valuable data, and then with probability strategy we add like an exploration component to this. So 0.8% of the times it is going to pick the node as given by the strategy, but 0.2% of the times it is going to explore randomly. For confidence based strategies, we focus on the high confidence nodes, as in like if we have an adjacent neighbors list and one neighbor in there is there like which doesn't have a high confidence of 1, then we remove that and we only focus on the nodes which have confidence 1. If there is no such node, then we pick it from the randomly from the complete list. And probability and confidence based strategies combines the above two notions. Also, I would like to add that the creation of chase enemy node and chase valuable data strategies have been inspired by the A-star algorithm, which is a heuristic based graph search algorithm. So in this case, we use the distance from valuable data or distance from the enemy node as the heuristic to select the next node. Coming to the Catch Me game Lambda, it as explained before, it is a Lambda function that uses grpc protocol buffers as its data transport format in the HTTP calls. And this is how we can build and invoke the function locally. So we use the SAM CLI, and we use an event.json to test it locally, and then once it works locally, we deploy it on the AWS. Coming to the visualization tool, the visualization tool is like a simple HTML, CSS, JS application that uses the D3JS graph library for graph visualization. So this GIF is like is an example of how the graph can visualize, but we'll also look at it in detail later. And then these are the instructions for running the visualizer. So I would like to do a quick run through my code. So this is the quick start app.scala, which starts the server for Aka HTTP. We started on port 8080 on 0.00. This is my JSON formats file, which is basically the serializer deserializer file for my classes. Then we have the routes file. I have created like multiple routes in this file, as we saw like init, reset, action, etc. So these are all the functions that we create to for Aka actor system, and we use like the ask reply pattern. I have also added like authentication to some of my APIs. So as you can see, we are using the authenticate auth2 function here. And yeah, now this is like the coming to the registry class. So this is like another object required by Aka HTTP. So I created this using the reference of the user boilerplate code that Aka provides. So as you can see, we are using the reply to pattern here. Then this is the so this is the game environment file. We are using like case classes enums to make the environment. This is the complete environment, and it follows, as I said, it follows the creation of it's inspired by the gym environments from the gym repos that RL training uses. So yeah, this is the Lambda invoker. So because we use this to call the Lambda whenever the game ends and somebody wins. These are all the functions that are required by the game environment. So we have like check game over, get agent data. We have like action function. We have init function. And I would like to add that the init function uses the path for graph files. And these graph files are generated by the preprocessor, as I have used in the older homeworks. Also, this is the Lambda invoker, which basically encodes in the protobuf format in our Scala server, and invokes the Lambda function, gets the response back, and then decodes it back to the data that we need using the protobuf specification, protobuf stubs, basically. Yeah. And these are the stubs, like these are the classes produced by the protobuf when we compile the protoc file using the proto compiler. And then let's also see the Docker compose file. So this is my Docker compose file. It has like two services, the server and the Nginx. Nginx is used to reverse proxy the server to port 80 on EC2. This is my Docker file. It uses an image with JDK 17, and this is my Nginx config, which is basically like reverse proxies the Aka HTTP server to port 80. Now let's see the code for the client. So this is the main file of my client, where we can provide like the API URL, strategy names, number of turns, and number of times to play the game, and it starts simulating the game for like sim iters, and then aggregates the result and prints them to the console. The initialize game function like does the init call to the game environment. These are the multiple strategies that are supported by this client. So we have created like multiple strategies as described before. This is my run game function, which runs my game, creates strategy and creates agent. So we have used some OOP here. Basically the agent is a class, and we have some strategy class. So agent uses a strategy class uh, to function, and then we have multiple base strategies which are then extended by the probabilistic strategy or the confidence strategy. So this is a request helper that I created. It basically uses generic programming to help me with the get and post calls that I make to the API. And then this is my agent class code. As you can see, we have like strategy. It's a base strategy class, and we use some functions from it. And then we have like strategies object, which has the base strategy, which is like the base class used to define multiple strategies later. Coming to the EC2 deployment part, so let's go to the instances in EC2. I already had created an instance which I had stopped. So let's start that instance, and yeah, let's wait for it to start. Meanwhile, I can talk about the configuration of this EC2. So I am using a T2 large instance. It has, yeah, these are all the parameters of AWS. I'm using like a Ubuntu Jammy 22.4 OS on this. And yeah, I guess that's it. So now that it has started, we can connect to it using the SSH. I already have the SSH key downloaded. That is like when I created this instance, I downloaded it to my system. So I'll open up a terminal and SSH into this instance. And yeah, right. So we are into the SSH into the instance that we have created, and I'll go to like my REST API repo and pull it. And then I'll do the Docker Compose build and Docker Compose up. But I have already built the images, so I guess I'll just do the Docker Compose up here. And that is going to start my APIs. So this has started my API. As you can see, the logs of Nginx and my API server have started to come in. And yeah. So it takes some time to compile and start the server, but it is going to start soon. Let's test this API with Postman. So I'll copy the public IP that is provided to my instance and use this in my Postman calls. So yeah. And then you're going to see that I do these Postman calls, and I'll speed this part up. Postman also provides like a good functionality to auto-generate documentation using the API tests that I just did. So this is the documentation that I've generated for my API. The URL for this can be found in the. Now let's see how the client works. So I'll go to the client, edit the config. So I have changed the API URL to my deployed API, and then I'm going to change the strategy. So let's start with using the random strategies first. So both the agents are going to use a random strategy, as in they select a random node from the list of the adjacent nodes, and let's simulate this 20 times. So I have changed the config IntelliJ, and I'll just start the program. So it's compiling and it is going to start, and it's going to start requesting. So as you can see, it has started simulating the game 20 times, and all these logs are coming in, and we'll get the statistics soon. So I do this for multiple strategies. So we have different strategies like random, chase enemy, chase valuable node. The thief usually uses the chase valuable node strategy, and the police uses the chase enemy strategy. These are informed strategies. I added like a probability component for exploration, as explained before, and I also added like the confidence score and confidence score integration to these strategies, where the agent only focuses on confident neighbors. Yeah, so I'll speed this part up and we can look at the results towards the end. Also, like I said, that we have a invalid move makes loss flag, which means that if the agent makes an invalid move, that is, it selects a node which is not adjacent to it, then it loses the game. So I'm just going to the API, going to enable this flag and test out some more strategies, and we'll see how it makes a difference in the results. So this is what I'm doing right now on the screen, and yeah. So this is my game visualizer. As mentioned, it visualizes the log. So I'll open the graph file first. This is my edges file as created by my preprocessor, and then I'll open like a random run log. So that's what I'm doing right now, and yeah, and then we can start animation and we can see how the agents travel. Uh, you can like view different logs and view this. So this is like the speed up footage of it, and yeah, here we go. Here, I would like to explain my Lambda functions code. So this is my proto file. This is my application.py, and we have the grpc encode, grpc decode function, which encodes our data into like the protobuf format and like a base 64 encoded string, so that is easier to communicate between the server and Lambda. And yeah, we import the proto stub generated by the proto compiler. And in the Lambda function, we like decode the data, store it in a S3 file, and then send the response back. So this is the file which is generated by the protobuf compiler, and this is the template that we use for the serverless application. So we have like a serverless function. We create some policies to provide permissions on our S3 bucket. We create certain events, and yeah, that's it. And this is how the Lambda works. On the server, if there is a winner, we invoke the Lambda and it stores the winner on the winner count on the S3 file. So let's see if the Lambda actually works when we run the client server. So let's check the win counts in wincounts.json at this point. So it is like police is 80, thief is at 74, and we have like 5 ties. And yeah, and let's run the client program once and see if the count changes or not. Yeah, so as you can see, there are 3 wins for police and 4 wins for thief. And now let's download the wincounts.json again and actually view if it is like that. So yeah, police is 83 and thief is at 78 now, which means that our Lambda function actually works. And so this is how you would actually build a SAM application, which is like serverless Amazon application. And I have added the use container because it's easier, and it uses like a container to compile everything up. And I'll speed this up, but once the build is complete, we can like invoke it locally using the local invoke with the use of an event. To see if the Lambda function actually is behaving like we want it to, and then after that we can deploy it using the deploy guided command, and it asks us like a whole lot of details about regions and configuration that we can provide to it. On to the results discussion. So we can see that the random strategy like police wins more than thief, and it has like a high number of average turn. This means that obviously they are working with like no information, and since there is only one valuable node in the graph of 100 nodes, that's why thief has won less time than police. In the informed strategies like chase enemy and chase valuable node, we see that it's almost equal, like police is 11 and thief is 9. and average turns is 5. This is because they are taking informed decisions and traveling the graph with like information and taking the ideal moves. And in case of probabilistic chase enemy and chase variable, we see like the same result, but the average turn has increased because the node, like the agents, they explore more. And in case of like chase enemy confidence, chase valuable confidence, the thief wins more because it doesn't make a lot of like invalid moves, and then chasing becomes difficult because the thief is also always moving and the police is also always moving. And then in probabilistic confidence with informed decisions, we have like equal results. And with the invalid loss flag on, we can see that the average turns decrease than random, because like the agents are prone to make an invalid move and then the game gets over. So thanks for watching.